So we're just, I mean, this is the materials review section. Materials in terms of the FE's definition is not really what you think of when you think of materials that you've been studying. Because it goes back more to like mechanics, materials, or that kind of stuff. There is a little bit of civil engineering, construction materials in there. So we're just going to kind of go through, I guess, the basic materials questions that they have in terms of mechanics materials, and then some kind of review on construction materials, like what you're used to. I'll go ahead and say it now. I don't know what everybody else has been telling you, but as far as studying for the FE, this review book or manual thing, reference handbook, know that thing front and back, because that's what will help you. I mean, that's what's going to save you in the test. A lot of the questions that they ask are not questions that you're just going to have to know stuff from your 4 years or whatever here. A lot of them are going to be based on, you have to have enough knowledge to be able to use what they give you in the handbook and then do something with it. So if you don't know anything, you'd be a creep. But for the most part, it's not just going to be a matter of recalling stuff. So in this book, it is not laid out the best in terms of like grouping things. They're kind of grouped, but not really well grouped. There's a lot of definitions in here. There are equations that you wouldn't expect, or it would be an equation that you could use for like a aggregate question, concrete materials or asphalt materials question. That would be in the foundations and soils set of equations. So if you know where it is, and you know, especially like kind of the headings and just the equation, this is an equation for X. As you come through the test, you'll see stuff, you know, it'll say, given this, this, and this, how would you calculate this? And it'll make it a little wordier so it sounds like a real problem. But if you know what that keyword is, or kind of have a category for where it falls in the book, a lot of times those kind of things will help you out a lot more than you think. So I think this probably points to some of those types of examples. We'll just kind of go through it and I'll show you. All right. Usually this is in a room where we have a projector. I guess we do have a projector, but we usually have like a little writing camera thing. And so it's a lot easier to do this. Do y'all want me to write on the chalkboard? Or just tell you things and you write them down. And I'll write down a specific thing. I'll write on the chalkboard for like equations or diagrams or something.
Yeah, sounds good.
Okay. Most of everything you need is in that book, and all these little blank spaces will give you space to write.
Can you pass one back?
Yeah. Just one?
Yeah. Appreciate it.
Okay, so this first problem, have you seen anything like this before? Probably not. If you haven't done anything like this in any of the classes that you've taken so far, this would be definitely like a mechanical engineering type class. It's like a fraction mechanics type problem. It looks difficult. You've never seen it before. You have no idea what it is. But if you will turn page 105 in this handbook. See something familiar?
Oh yeah.
Same exact diagram. You'll come across stuff like this. Maybe not, they won't have the diagram drawn necessarily, but it will talk about this concept. If you're familiar with this little section in the handbook and you see this problem, you don't have a clue what to do, but the problem is actually pretty simple. So you're given this equation here, this K sub I equals something. That K sub I is what you call a stress intensity factor, and it's basically more or less a constant for a given material. And you see the top right of the page, it's got a little table of different materials with these different fracture intensity values. So the question that we're asked is, we've got a brittle material with cracked the edge, and it's in tension. It's 100 millimeters wide, it's got a 4 millimeter long crack. The question is, what type of material can be used to avoid catastrophic crack propagation under the given geometry and loading condition? Crack propagation just meaning the crack's already there. Basically what stress intensity factor do you need to keep it from growing? So if you take what information you're given and plug it in this equation, you would get, let's see, so you have Ki equals Y times stress times the square root of pi times A. The Y geometric parameter, which one do we need? 1.1. And then the stress, that would be, well, actually, yeah, we're given the stress. It says force there, but we're given stress. So we're given stress of 200, and the A would be the crack length. If you notice, this is where the FE gets you all on a lot. This kind of stuff that you just got to be cautious of. What are the units of the KI value?
MPa times meter.
Yeah, and we're given millimeters. So little things like that, if you're flying through that test and you think I got 2 minutes to answer this problem, you'll blow right past that and you'll get it wrong, just because more than likely they probably got an answer there that would be the answer if you calculated it with 4 instead of 0.004. So if you plug everything in, we got 1.1, we've got 200, and we've got square root of pi over divided by 1,000 meters. And somebody calculate that? 24.7. So that means is we need a material that has a stress intensity factor of at least 24.7. Anything less than that is going to continue to crack. Anything greater will be okay. So given that number, what material will we pick? Huh?
A1 2024-T3. Or, I mean, could you consider the 24.2 close enough?
I would, well, this is kind of cut and close. A lot of times the FE is, I mean, they're pretty generous on the rounding.
Yeah.
So that, the FE, that might be okay, but we'll just say for now, we have to have this amount for it to not crack. So we could use the A1 2024 T3 or the 4340 steel. Either one, we got 44 and we got 46. They're both greater than 24.7, so we're good. Does that make sense? Mm-hmm. So it's a pretty simple problem. It's just a matter, it really is just a matter of knowing where to look in this book. All right. All right, take a look at the next page. A little refresher on stress strain diagrams and all that. You've got, let's see. All right, so if I were to, again, this is pretty elementary. When they would ask it on the test, they would be a little more confusing sounding. But if you were asked to define engineering stress, what would you say? stress is what? Load divided by area. You've got a bunch of different stresses on this stress strain diagram. So if we just think of regular engineering stress, what you're used to calculating is
Ultimate?
It's elastic gauge.
nope, just force divided by area. As that thing stretches and you start getting into these crazy parts of the curve, what do we assume? Does the area change, or does, I mean, in reality, what does it do? Area would change because it's being stretched. Engineering stress just calculates whatever the stress is, or whatever the load is, divided by whatever the initial area was. So that's fine for the most part, as long as you're in that elastic region. Once you get out of that, then you start having changes to your cross-sectional area. So we're so used to just calculating engineering stress that you just say force divided by area is your stress. But when they talk about materials, a lot of it gets out of the normal, like, you know, you got concrete or you got soil loaded or whatever, or steel beam, it gets into these crazier regions. So if you've got engineering stress would be force divided by, or load, either one, divided by the original area, and then the strain would be, you know, it is
Length divided by original.
change in length divided by the original length, yes. So you got change in length divided by the original length. In reality, strain is not quite that, because when you use these original areas and these original lengths, it changes a little bit. And so if you were to say the true stress or the true strain, you would take that off, and now you're talking about the actual stress or the actual strain at that given point in time, wherever it is on this load deflection curve or stress strain curve. Questions? All right. Not having a little document form is not easy. Okay. The different sections on this thing, elastic, that's what we typically deal with as civil engineers. You know, when you do steel structures or concrete structures or whatever, you don't really ever think anything beyond that. Elastic basically just means that the law that modulus is stress over strain applies. Basically, modulus is the slope of that line. When you get into the yielding phase, as you can see on this diagram, you're straining more and more. You're getting further and further to the right, but you're not increasing stress. The reason being, or during this stage, it's just plastic deformation, I guess, where the particles themselves are realigning, and they're kind of shifting so that it's just stretching without adding anything else. And then you go into the strain hardening zone, where now everything's kind of reset itself, and you start taking on stress again. And then the point where it's just failures occurred and you have a backing issue. You can see fracture stress and true fracture stress. You've got those two lines there. One kind of keeps going up, the other one drops back off. That's a product of this equation. Because your fracture stress is a little lower always, because it's assuming an original area. Say the original area was 1 square inch. The true fracture stress is taking into account the instantaneous area. So as it's stretching, the area may drop to 0.96. So if you've got stress equals force over area, stress goes up because the denominator went down. Makes sense? Is this like on a good level, or is this too much, too elementary? Whatever. Okay. Just tell me if you want me to adjust somehow. So basically, when you see those two lines that take off different directions, we just say that the engineering stress, the ultimate stress, and factor stress. That's what we would calculate because we're using the original area and all that. And then eventually the thing breaks. You have seen stuff break in the lab or somewhere before. Same as that picture. Any questions about stress strain curves? Something in this book that I was going to point out. I've seen questions before sort of dance around this. Alright, and on page 33, there's an equation that says percent reduction in area. And sometimes we'll see questions that will say something like, if the engineering stress is, say, is 100 psi, and you have a reduction in area of like 80%, then that reduction in area is calculated by this equation. It can be used to kind of back calculate. If they might say, all right, given this, what is the true stress? There's no equation for that in this book, but it kind of goes back. If you can just think about, which I guess is why we're going all over all this stuff. If you can think about what the fundamental part of it is, if you got this much change in the area, then an equation like this would apply. So your true stress would just be the engineering stress divided by 1 minus RA. So you got 100 divided by 0.2 basically. And so, what was it? Probably something I should know. 500. Does that make sense? It's just little manipulations like that you may see some of those kind of thrown in there, that they give you enough information to kind of take it and run with it, and you kind of have to process through what it's asking and how you could get to that. So, all this does is basically saying, now you got 80% of the area gone. You only got 20% left, so your number is going to increase by that much. Or you can think about it, if you go back to 100 psi, say we had 1 square inch, and then we lost 80% of that, now we're down to 0.2 square inches. So this is your load divided by your area, and you're at 500 psi. So they'll give you equations like that, and you may not really have seen reduction in area, but you can, again, just knowing kind of where the stuff is, you'll be able to reason through it. All right. Any questions on that? Okay. Next page. This is, for those of you that are in Pavement or taking Pavement, have seen this. This little diagram at the top is basically just a example pavement structure. Now, if you, this is in the book on page 166. They got the equation and nothing else. Now, I guess since I am a materials guy, we'll break it down a little more. You remember what the structural number is? basically the capacity of whatever that structure. So you need a certain structural number to protect your subgrade for whatever traffic conditions, environmental conditions, or whatever you've got. So if we look at this pavement and we wanted to calculate a structural number, it's pretty simple. As far as these A terms, they don't give you a table of that. If they would give you that in the test, I don't know. But they're typically 0.11, 0.14, 0.44. 11, 14, 44. For your subbase, base, and an asphalt layer. Those are based off, can you tell me? ASHTO road test. Those are based off the ASHTO road test. And so they're empirical, they apply only to that one thing, so they're not hard and fast numbers by any means. But that's, I don't know, if you have to remember something, that's a good number to remember. And then, so this only deals with everything above the subgrade. The structural number, like I said, is to protect the subgrade. So you would base subgrade and traffic would tell you what your structural number needed to be. You would go through and adjust all your layer thicknesses until you calculated a structural number that was greater than what you needed. So that is pretty simple.
Would you say that A number is typically
11 or 0.11, 0.14, 0.44. People, you may or may not see like something like this, but people have a lot of different correlations to other properties for these structural coefficients, the A's. And so you can see that here. Then at the bottom, we got the structural number determination equation, where it's an iterative type equation, but you put in your predicted traffic, would be your W18, the number of easels, the ZR, SO, that is, anybody know what that gives you? It's your reliability. So that wasn't in the original 72 ASHTO guide, it's in there now. And then you've got these other random little segments. Then you got the log of NR down at the bottom. That wasn't in the original 72 guide either, that was something with weather or account for climate stuff. So basically, if you just cut out the ZR, SO, and the MR terms, you're back to the 72 guide. So if you add them back in, you're up to what they do currently. Just so you can distinguish between the two. On the next page, we'll just kind of run through a quick analysis problem with this. And again, whether or not this exact problem, or like a problem like this, that would require the use of all these other tables would be on the test, I can't say. But this type, this like, what do you call it, structure problems definitely would be. So we're given layer thicknesses. We've got 4 inches of asphalt, 8 inches of base, 12 inches of subbase, and then we're told some properties. So we're given an asphalt resilient modulus of 450 psi. We need to get an A term, a structural coefficient term from that. If you look at the page on the, or your last page, you might take a stab at that.
Look at the Pronestian value. What you asked for?
Oh, no, I was looking for the layer coefficient, the A term. using the modulus.
2.43 or something.
Yeah, so that'll work. I mean, we'll just call it 0.44, just to stick with the typical value. But they'll have stuff similar to this, where you just kind of got to go look at the values and use stuff like that. What about for the base and subbase? The layer coefficient for base CBR on it. Look at the handout. It's not going to be in that book. What one for? And also, do you remember from Soils or Materials Lab? I don't know which one. When you ran CBR, what is CBR of California limestone? Huh? 100. You also notice that 100 corresponds perfectly with 0.14. You see a lot of that kind of stuff when you look at this. So, it may not be useful, but you stuff to keep in mind. So we'll call our base layer coefficient 0.14. What about for our subbase?
Something less than 0.11.
Yeah, 0.105 maybe.
Yeah.
We'll go with that. All right, so at that becomes really easy to calculate. Our asphalt was 4 inches times 0.44 plus 8 inches times 0.14 plus 12 inches times 0.105. What's the structural number?
4.14.
Sounds good to me. Alright. That is an analysis problem. We didn't design anything. Make sure that you just kind of keep the difference in your mind. Because if you were designing stuff, you would take this equation and work backwards and take your required structural number, say it was 5, and then you start back calculating all these different layer thicknesses given these coefficients. And you would have to end up with a number that was bigger than 5. So right now this road like we have it would not pass. We have to increase something. So just make sure you keep those separate in your mind whenever you're doing analysis and design. We would, if we were designing, we would take an equation like that long equation on the previous page, or some kind of, you're on nomographs or, well, it's similar to this chart at the top of the page. Some kind of crazy, like, you start here, you go a line up, and then line down, and all that. You figure out your required structural number. Like I said, it's based on what thickness of road you need to protect your subgrade, and then you would, yeah. So, any questions on that? All right. Next page. What's the difference in the water to cement ratio for an air entrained and a non-air entrained concrete specified to have a 4,000 strength or PSI strength for 28 days? Any shot at how you would tackle that? Yep. And that is all seriousness. Anybody know where you would go? Page 10, nope, not that. Page 106. This goes back, like I said, the book doesn't seem to be the best laid out because you would think concrete, civil engineering, is in the materials. So kind of know the difference on this, because otherwise you would probably have no idea how to answer this question. And if it wasn't in the civil engineering section, you'd say forget it, I'll write B down and move on. But this little figure down at the bottom right of page 106. Can anybody answer the question now? Take a look at the question again. What is the difference in water cement ratio between the two mixes?
Probably like 0.05.
What did you say?
0.05, something like that.
Yeah, about 0.05, 0.06, something like that. Super easy problem. There really are a lot more of these than you think on the FE. Maybe not quite as gimme as that one. I might actually calculate something, but pretty similar stuff. There's stuff that you're like, I don't know how to calculate that. And there's some pretty simple thing in the book. Also, notice that above that whole figure and below it, it gives you decent descriptions of what all these things are, just in case you didn't know. You probably would know for something like concrete, but if you get into another, say, circuits or something like electrical engineering thing, it's just outside of my understanding. They'll have definitions and stuff like this too. So, like I said, know the book. Another question that could have been asked from that is something like, what would be the expected compressive strength of a concrete mix with 0.5% water or 0.5 water cement ratio cured in air versus cured in water for 20 days? And this chart at the top left, that's why these kinds of things are in there. It's just kind of, they give you enough information that you can go and kind of figure something out off of it. And because if you think about it, why else would they put a chart like this in here? It's not just for you, FYI, in the middle of the test, that concrete cures differently. It's probably going to have some question that graph would be used for. Otherwise, they probably wouldn't put it in there. So that's a pretty easy example. Next page. Alright. Is anybody confused about specific gravities on aggregates and all different kinds? Bulk, SSD, oven dry, all that different stuff. Aaron? Nobody confused? Good. Okay, we can skip it if you want. Go ahead. Alright, well, first. Alright, so we're about to write down a bunch of equations. You're not going to memorize these equations. But if you know, again, if you know the fundamental behind it, if you know what bulk SSD is, or, sorry, not bulk SSD, if you know what, well, I guess, yeah, bulk SSD, or if you know what oven dry means, you can calculate all these things. Look in the beginning of the civil engineering section, which is like page 130, 130 something. 132. Alright, it starts off with geotech. There's this equation probably on the page that says specific gravity of soil solids. The way the solids are volume of solids divided by unit weight of water. Specific gravity is a pretty easy equation to remember. So you can probably remember the general form, but it's got a bunch of other different equations. And so things like this, if you can remember just what oven dry specific gravity means, that you're talking about a dry aggregate, so you got a dry mass, you got a volume with no water in it whatsoever. It basically means what this equation is right here. But then if you've got an SSD, now you've got to take into account the weight of the water and all that stuff. And so all you got to do, if you know what you're looking at, is just add weight of water to weight of solids. Makes sense? So again, that's helpful. All right. As far as the different types of unit weights or specific gravities, you've got apparent, is that dry or wet?
Dry.
Does it matter? No. All right. So it doesn't matter because water is not included in this calculation. You've got weight of solids over the volume of the solids. And actually, let's write this in terms of you got weight of the ag, you got volume of the aggregate over unit weight of water. So you're not including any of the pores. So you're literally looking at just what the specific gravity of the rock substance is itself. Does that make sense? Then if you go to bulk, you've got two different types. And those are anybody? Oven dry and
Saturated surface dry.
SSD. So you got bulk. By definition, what does bulk mean? What's now added in? Voids? Voids. Voids are never calculated in specific gravity calculations. At least not in these. So you got bulk, specific gravity. We'll say oven dry. You've got the weight of the aggregate and nothing else because there's nothing else in it. But now you're looking at the volume of the aggregate plus the volume of the pores, again divided by the unit weight of water, and you got that. As you were doing the same thing, but with the SSD, now you've got the weight of the aggregate plus the weight of the water that is in the pores, and then volume of the aggregate plus volume of water divided by unit weight of water, change from unit weight to the specific gravity. Going back. All right. Then, and you remember the difference between pores and voids, correct? Okay. And when let's see. All right. What if I think look at the next page. Hopefully this is not something you really need to review anyway. You got different aggregate states. You got oven dry, which would be that case. You got SSD, which means the pores are full of water, but no more. You got in between, which is typically air dry. And then you got damp or wet, which you got water. You got too much water in there. You can see on there, total moisture would be the weight minus the weight of oven dry, divided by the weight of the oven dry, times 100. And say that you're, okay, and then you got absorption, and you got surface moisture, which would be the total minus the absorption. Say you've got an aggregate that has a absorption of 2.4%, and you take the water content of it, stick it in the oven, and you measure 1.8%. You use that aggregate in some kind of mix design. What then? Yeah, count for water absorption. You're going to have a lot of water going into the pores just because the pores aren't satisfied yet. They're in that air dry state, which is, like I said, more or less what all aggregate is at. And you probably won't have this question, but I think it's good practice. With concrete, do you have to adjust for moisture? For asphalt, do you? Because there's no moisture in there, you burn it all out. So this only comes into play with concrete. So when you think of specific gravities, a lot of times concrete plants will use different specific gravity, or they'll mean different things depending on who you're talking to. Make note of that. Let's see. All right, we good on that? Okay. You want to do mix design real quick? No? All right, let's do one. Do you remember the basics of how to do a mix design? They would never ask you to do a full mix design, but there may be snippets here or there. Basically, you're going to be given, we've got an example problem here. You're going to be given some properties. You want a certain strength, you want a certain workability, you want a certain durability, and a certain economy. So for strength, you got 4,000 psi. For workability, you got 3 to 4 inches of slump. For durability, you got 6% air. And for economy, you've got 1 inch max coarse aggregate. Remember that? So then we're given the properties of the aggregates, and from there we just kind of take it and run with it. There are some tables included in here, so we can walk through this pretty quick. Let's see. Let's say that. Alright, let's coarse aggregate. A good absorption for kind of gravels we got here. 30-something%, we'll say that. Fine aggregate, you think it's less or more? Anybody? Less. We'll say 1%. Alright. So, you've got tables in the next couple pages. These are the same tables you would have seen in that concrete BCA manual that you were given materials. Where would we start? Any ideas on what we select first? We're given water cement ratio, but we kind of skip the water cement ratio step and jump straight to the amount of water we need.
Based on the slump rate.
Yeah, based on the slump. We'll calculate water cement ratio later to get our cement content. I guess you could do either one first, doesn't matter. Alright, so you're right. Well anyway, we'll do the water first. So we got 1 inch aggregate, look at that table at the top. We got 1 inch aggregate, we do have air entrainment. We want to slump to 3 to 4 inches. What's our target water? What is that? Gallons? Pounds. 295 pounds. What do we do next? cement ratio. So we got air and train of 4,000 psi concrete. So what would our water cement ratio be? 0.48. So we've got water cement equals 0.48. So if we want to calculate the cement, we say 295 divided by 0.48 gives you, somebody calculate that?
$614.6.
614. Let's go with that. So now we got our cement. All right. Then what? Fine aggregate? Yes? No? Coarse aggregate. Yeah. Fine aggregate's always last. It's just a filler basically. So we take our fine aggregate properties and our coarse aggregate properties. We are given a fineness modulus of 2.85 and maximum size of 1 inch. We'll say nominal max. So our bulk volume, the coarse aggregate would be like 0.665. You want to get fancy. And then we're given a coarse aggregate dry rotted unit weight of 98.5 pounds per cubic foot. That would simply just be coarse aggregate, what is this, 0.665 times 27 pounds per cubic foot times, what is our unit weight? 98.5? What's that answer? What that should be?
I'm not sure where you get the 0.665.
27 feet cubic yard.
No, because you're looking at a unit weight. So this is pounds. I put it down wrong. Pounds you get foot. This one and this one cancel. And you're left with pounds. This 0.665 thing came from this table. Table 9.4 in the handout. And all it is just a. It's kind of
1 inch, right?
Yes, 1 inch. So we're at 2.85 on the fineness modulus. So we're somewhere between 2.8 and 3. So if you just kind of interpolate between 0.67 and 0.65, you end up with 0.665. We're good on that.
Just for a yard or cubic yard?
Yeah, concrete is always designed around a cubic yard. And then you scale up or down depending on how much you want to make. Anybody have that number?
1761.
1761?
69.
1761. Alright. So, any idea what we do now? Not yet. Calculate the volumes and all those different things. So, water, 295 pounds. That would be convert that to cubic feet. feet gives you how many cubic feet of water?
4.8.
4.8. Oh, no, that's wrong. Sorry.
4.7.
Alright. And then for the cement and coarse aggregate, we know there's specific gravities. Specific gravity of cement. Anybody? 3.15. So just 3.15 times the 62.4 to get the unit weight per dip. What's that number? .1. Alright, and then the coarse aggregate, we're given a specific gravity 2.67. And so that is what? Oh, sorry, times
10.6.
what?
10.6.
Alright, so now what's next?
There.
Air. Alright, so our air, how much air do we have?
6%.
6%, so that is just 6% of the total volume, 27 cubic feet, which is what?
1.6.
1.6. Okay, so now the only thing we got left is the aggregate. How do we get that? This is the easiest one. 27 minus all those things. So somebody figure out what it is.
7.
7?
Yes.
Even?
7.
Alright. So now are we done? Nope, absorption and stuff. Alright, so if we've got an absorption, let's see.
27 cubic feet.
We weren't given water constants. Were you given water constants?
We got some
Oh, okay. Alright, so 5.2 and 6.5. So alright, so are we gonna have to add more water or take water out?
Take water out.
Take water out, yes. So in that case, up to this point we're clear though, right? These are just the target values. This is assuming that aggregate absorbs nothing or has nothing to offer in terms of water. And so this is basically just the water that would lead to the water cement ratio of 0.48 that would lead to the strength we need. It's just enough water to react with the cement. But now we need to account for that one way or another. So if we've got the batch weight, say if the coarse aggregate is what we want to find, this is how much we actually need to batch. So we've got 1769. Yeah, 1769. But if we batch 1769 pounds, is all that wrong? No, because we got free water, so some of it's water. So then we want to account for that. So we just simply take how much water we have left over, or that's in the rock, and multiply it by that number as well, and then add it to it. So we got 0.052 times 1769 gives you
It's not made of full moisture.
no, this would be because you're batching, so you're assuming here that this is completely dry. If, and this is where it gets tricky, these specific gravities, we're assuming that's an oven dry specific gravity. I don't know if it's said or not. It is? Yeah, so they are oven dry specific gravities. So anything in excess of that is going to be added on, whether it's free moisture or absorbed. We won't have to worry about that until we adjust for the water. Yeah. So, so we have this number?
1861.
All right. So to get that much actual rock, we have to batch that much out of the stockpile, and some of it's water. So we do the same for the fine ag, which we don't. All right, what would this be in pounds first? It'd be 7 cubic feet times 62.4 times whatever specific gravity is.
1157.
1157.
1157.
1157. Alright, so now we got 1157 plus 6.5. That number? $12.33. Alright, so that's how much we need to batch for our aggregates. Now we gotta adjust the cement for its moisture content, right? No, of course not. That's how I would do it. Anyway, that's what I love. Yeah. Alright, so do what? Yeah. What did I say? Anyway. Alright, so now the only thing we got left to do as far as our moisture adjustments is the free moisture. So we would just take basically figure out how much water weight is in that difference between 5.2 and 3.2. So for your CA free water, I guess we'll call it, you've got 1769. 0.052 minus 0.032. So basically 2% of that would be your free water. Do you have a number? 35? Alright. Then for the fine aggregate, we've got 1157.065 minus 0.01. Yeah, that number? What?
25.7.
25. Alright. Why do we use these weights as opposed to these weights? This is the kind of stuff that'll get you on the FE. Not how to do the work, but little nuances like this. Any ideas? All we're doing here is calculating absorption, which if you wanted to, this may have been in here and was stupid or something. I don't know what doesn't do it, but going back to that. This thing here. The absorption is relative to the oven dry weight of the rock. Correct? So when you say it's got 1% absorption. That means if it's at SSD, you got 100 pounds of sand dry, you're now weighing 110 pounds or 101 pounds, because 1% of that is water. Does that make sense? It's by weight and it's relative to the dry mass of the rock. Makes sense? So when you say this over here, and we're trying to figure out how much water there is, we're trying to figure out how much of these there is, but it's still relative to the dry weight of the rock, just by definition of the equation. So that's why you would come back and use these numbers. So then what would we do with these two?
We would take that amount. We would reduce our added water by that.
Yep. So we had 295 pounds, subtract out 35, subtract out 25 and a half, and what do we get?
So you just subtract out those numbers, is that what you said?
Yeah. Water. 234. And the cement doesn't change. So this would be your final mix design. Water just went down. Coarse ag and fine ag went up because the water is in them. Easy enough. Alright, and how much volume is that? 27 cubic feet. So if you wanted to do something different, you would take those numbers and adjust. Divide by 27, multiplied by whatever. Any questions on that? Okay. Alright. This is much more likely to be on DFE. Do you know how to do this problem? This load equivalency thing? Alright, look at page 166 in your handbook. So what we're given here, we're asked to calculate the easels for basically the following payment. It had a AADT, average annual daily traffic, during its first year of 12,000 vehicles in both directions, with 50% passenger vehicles, 33% two-axle trucks, 17 three-axle trucks, and their pounds per axle is right over there. And then we're basically going to take this, stretch it out over 20 years, assuming a 4% growth rate in traffic, and that you got a lane factor of 0.45. The basic equation for that is growth. You've got the daily traffic, but it's annual, so you want to do it 2 times a day to get it into, or what, sorry, it's the average annual, but it's daily traffic. We want to look at this over spanning 20 years, 1 year at a time. So we say 365 times the AADET, and then times the number of axles, times the load equivalency factor. Okay. So some of these things are kind of easy to put together. Basically, we're going to have 1, 2, 3, 1 for passengers, 1 for 2 axle trucks, 1 for 3 axle trucks. We'll sum them all up at the end. So we got equals for passengers. We got equals for 2 axle trucks. We got equals for 3 axle trucks. Alright. What are some things we can go ahead and knock out easily? What about our design length factor? What that's given to us is constant for all of these. Alright. What else? AADT. Well, we're given that. What did you say? Well, alright, what's your growth? Not exactly. So we'll come back to that one. What would go in this blank here? 12,000 times whatever vehicle we're looking at, percentage, whatever it makes up of the total traffic. So for the passenger vehicles, we have 365 times 12,000 times 0.5. About for the 2 axle trucks. 365 times 12,000 times what? Is it? 33. And so that leaves 17 for the other. Alright, so that part's easy. Number of axles. This is easy. Passenger cars, how many axles they have? 2. 2 axle trucks. 2. 3 axle trucks. Oh, sorry, I'm around 1. 2, 2, and then 3. Alright, the load equivalency factor. You know how to calculate that? Yeah, that's where the handbook comes in. Alright, so for the passenger cars, we got 1,000 pounds per axle. What is our load equivalency factor? Yeah, a 0.0002. What about for our 2 axle trucks, which are 6,000 pounds per axle? Number? So the only thing left is the growth. It's 4% growth, but it's over 20 years. Just ring a bell. Anything that you've done in college, a rather annoying elective that you probably took, what? Engineering econ. You run all those tables, F given A given F, F given P, all that stuff. I know. That's what is required for a problem like this. It's in the book. It's just not in the transportation section, you might think. So it's not, flip right to it. Page 116. But we need page 118. So you go to this factor table, the one at the top on the left page. You see interest or growth rate equals 4%. And you got it over 20 years. So we're basically in the F given A case, that we're assuming traffic is going to be 12,000 year after year, but it's going to grow some. But we're putting 12,000 on it every year. So what would be our growth factor?
29.7.
Yeah, 29. What did I say? 0.78. 29.78. Same all the way down. Calculate these numbers. Can I get somebody to calculate first, and then the second, and the third?
I got a question.
Huh?
How did you know it was F given A?
It would be F given A because you got
Where are
annual.
those terms?
Do what?
Where are those terms?
Oh, okay. All right, so in these engineering econ terms, or whatever you want to call them,
116 over there.
yeah, you've got P, you've got F, you got G, and you got A. P would be basically like in terms of econ, would be a past deposit. So I don't know if you remember all the little like diagrams and stuff that they did in engineering econ, but it would be like you're at year 0. So we're at 20 here. So you put in some investment. This would be P. At the end, it's would have grown because of interest. So now you pull out F. If you were talking about G, G stands for gradient. So say you put in P here, and then you put in P plus 10, and then P plus 20, and P plus 30. You're not putting in a single amount once and getting it back, right? Our case is that we've got 20 years on this scale. So in year 0, we're putting in 12,000 vehicles. In year 1, we're putting in 12,000 vehicles. It just keeps going on. You got an annual deposit of the same amount of vehicles for 20 years. Make sense? So that's where that number comes from, or that's where that comes from. Any other questions about that? Anybody got any numbers? Do that. Yeah, okay, you get the point. So you take all these, add them all up. That's your expected, your predicted yields for that road. Going back to that long Astro design guide equation, the log of W18 equals something. This would be, sum this up, and that would be your W18. You put it into that equation to calculate the required structural number, and then you calculate your pavement thicknesses based on that. That's kind of how it comes. Got it? Any questions? All right. Gradations. Occasionally they'll ask something about this. Do y'all have any questions about these? This question here at the top says use graph provided to establish that this soil can be used if, or the criteria is that the CU over CC ratio has to be greater than 3. This one's pretty easy, not real tricky, because if you just go to the geotechnical section, you will find CU and CC. Calculate them off that thing, plot, whatever. For that, you need, based on
What page is that?
134. So to calculate those two equations, you need D10, D30, D60. Those I got defined here. Basically just whatever grain size it is that has 10% finer or 30% finer or 60% finer. So if you look at that, whatever, gradation there, and you go to the 60, go over till you hit the curve, go down, and you're at 0.1, 2, 3, 4, 0.48, something like that. Everybody see that? 0.48. Wait, what?
0.38.
You said 60%.
60%.
0.48, that's right.
0.48.
Yeah.
30% looks like it'd be 0.1 something. 10% would be about 0.03. Anybody who wants to understand that guide? Alright. So plug in the equations, calculate CU over CC. If it's greater than 3, you can use it. If not, you can't. So, I guess that's the kind of stuff we expect. Any questions there? Alright, this last stuff, asphalt. There's a small section of asphalt stuff in the handbook on page 160 something. 167 and 168. And then this handout that you got basic asphalt terminology, as well as phase diagram, binder grading, chart, and the same as book. What are there any particular questions about this stuff? Talk. Phase diagram. And all this terminology, these little symbols and stuff. V basically, V always means volume. M always means mass. G always means specific gravity. P always means percent. Now, the subscripts, if you're talking about aggregate, S means stone. So if you see G, S, specific gravity stone, and it'll have some sort of other qualifier. You got B, A, or E. So you got GSP, GSA, GSE, specific gravity stone, apparent, bulk, effective. You get the idea. The binder, you've got P or G, basically what percent binder you have, or what is the specific gravity of the binder. And then for P, you got PB, PE, PA, all those things. Percent binder would be the, you got 5% binder in the mix. That means that you got 100 grams of asphalt mix, 5 grams of asphalt binder, 95 grams is mix. What that 5% is out of the total mix. So if you say I got 100 grams of aggregate and I want 5% binder, it's not 5 grams, because that would give you 105 grams of mix. So now your percent binder is 5 divided by 105. Does that make sense? You don't want to write that down? Basically, if you say you got percent binder of 5%, that means 5 grams binder, and then 95 grams aggregate plus 5 grams binder. If you take that the other way, like aggregate absorptions, they're based on the aggregate mass, not the combined mass of the aggregate and the water. So if you, does that make sense? Like if you had a absorption for some, we'll just put S there, in stone, and it's 5%, that means it's 5 grams water out of 100 grams aggregate. See the difference? So there's little differences in the terminology. Make sure you keep those separate. However, PBE and PBA, this percent binder effective, percent binder absorbed, you got this aggregate here, and it's got a couple little Dr. Howard type orders on it. So if you cook this thing in binder and some of it soaks in to where you know, it kind of fills that little gap right there. Now you got some of that binder is absorbed. So the percent binder absorbed goes back to this standard where it's of the aggregate. You probably don't have no need to know that, but it's of the aggregate, it's not of the total mix now. So if you say we had 1% binder absorbed of the 5%, it doesn't mean that 4% is effective. It means that 1% of the rock weight is absorbed. So keep that in mind. When you go to the mixture of asphalt and aggregate, that's typically denoted by the M subscript. And so you've got GMB for the bulk specific gravity of the mixture. You've got GMN for the maximum specific gravity of the mixture, that kind of thing. Any questions on that? All right, another tricky thing here. VMA, voids of mineral aggregate, usually around like 17%, something like that. You see on the float, the little phase diagram, it's just the amount of anything that's not aggregate. VFA, however, is usually like 65%. That's because VFA, if you look at the phase diagram, is voids filled with asphalt, and it's most of the voids themselves are asphalt. So it's not out of, so it's basically VFA as a percentage of VMA. So that means 65% of the 17% voids is asphalt. Let's see. Y'all know how to read a binder grading chart? Do you want to know? Yes? Alright. So when they go to the graded binder, they're going to run several tests on it. They're going to run flashpoint, which is just a safety thing. They'll run it at this 230C that you see here. It goes all the way across that chart, and it just has to meet that. That's just it's a safety spec, basically. So to make sure it's not going to blow up on anybody. The viscosity right underneath that is always running at 135 degrees C, and it has a maximum limit of this 3,000 CP centipoise. All it's saying, and that's for pumpability. They got to be able to pump the stuff through the plant. So if it's too viscous or thick, they can't pump it. So that's what that is. Basically, every binder's going to pass those two things, which is why they go all the way across. Then after that, you run basically 4 different tests. Are y'all familiar with DSR? Have y'all talked about that in materials? What a DSR is? It's basically just, you put a little hockey puck kind of thing in binder, just like an inch in diameter between 2 metal plates. They rotate back and forth, and it calculates a bunch of stuff. And it gives you this value, G star over sine delta. G star is the modulus, the delta is the phase angle, which like for steel would be 0, for water would be 45 degrees, or whichever one. So it's just a way to kind of characterize the whole viscoelastic thing in binders. But it's got a minimum value of 1 kPa at these temperatures. So if they ran this test at 52 degrees C and it was only 0.7 kPa, they would say it failed this test, we had to bump up the next temperature and run it again. And then they would run it again, and then it would be, they would start it, they would have to work down if it failed a high temperature. So they'd have to go from 58 to 52 and then try to see if it passed there. And then they do the rolling thin film oven, same exact thing, except now your criteria is 2.2 kPa, because now you've aged it some in the thin film oven, so you'd expect it to be stiffer. So now, at the same temperature, they're allowing it to be the criteria, the maximum, or whatever, to be stiffer. That's how you get your high-end number. And you know, the high-end number is basically what controls your running characteristics, right? That's what this whole DSR thing does. So that's how you pick your high-end number. And then you pressure raise the stuff. You know what that is? Basically, you got this high pressure, high temperature, and you leave it in there overnight. It just dries out all the volatile, flexible stuff in the binder, and it becomes really stiff. That's to simulate long-term aging after it's been on the field for 5, 10 years, something like that. And you run DSR again at what they call an intermediate temperature. So, and they kind of pick that based on just the consistency of the binder when it comes in the door. But so say we'll do 64 because that's what we have in Mississippi. So say we pass 64 on the upper end, we run DSR on the lower end, the intermediate, and we have to keep bumping up until we pass. So if we start at 28, that would be like the best case scenario, that we get a really good binder at low temperatures. We start at 16. And if it fails there, you have to bump up the temperature. If it fails there, you bump the temperature until you have one that passes this minimum of 5,000. The criteria goes way up there because it's been long-term aged. And then last, you have the cold temperature. So you stick that in the DVR. No more, it just takes a little beam, binder, puts a point load in the middle, and just holds it there for a bunch of seconds. It measures the deflection, it calculates the beam's stiffness, and the M value, which is similar to the sine delta thing. And so you got a maximum stiffness of 300 and a minimum M value of 0.3. So you do the same thing where you just keep testing until you find the first temperature that this passes at. or the coldest temperature that you can go without failing. And you see, so take a look at -12 there. So if we pass at -12 and go all the way back up the top, the performance grade is 6422. The difference there is because they test at 10 degrees higher than what the actual spec is. There's some reasonings for that, but just note that if they say grade a binder and you get -12 down here, it's not going to be a 64 minus 12. It's 64 minus 12 minus 10 more, so 64 minus 22. This direct tension thing at the very bottom, they rarely run that, and I'd be surprised if they asked you about that. But if they did, it'd be the same system. If any one of these criteria fails, you have to go to the next temperature, see if it meets it at those, and if it does, you can claim it's that grade. So if you pass on the creep stiffness in the end value, but fail on the direct tension, then you have to go bump up the temperature grade, run it all again, and if it passed for all those there, then you're good. Does that make sense? This intermediate temperature, okay, so we said 6422 would be the -12 on the very low end. The intermediate temperature, it would also have to pass that 25C. So I said if it failed one of those criteria, it'd be if it failed at 25, if it failed at -12 for creep stiffness or direct tension, it fails across the board for that low temperature for the -22. And you have to do it again. Any other questions? No? Do y'all want to talk about this aggregate page at all or not? Just tell me if you do. I just don't want to keep y'all here. I don't have to.
I like to hear about it, I think.
You like to hear about it? All right. Let's see. Just kind of running through it. All right. Some things to note. That top right table, mixture designations. You've got the nominal max size. So the super page says a 9.5 millimeter mix. That means nominal max of 9.5. Maximum size, first sieve size bumps up after that. So for 9.5, the next one up is 12.5. For 19, the next one up is 25. It always falls in that order. The control points, I mean, basically just whatever the gradation curve has to stay between those points. So for 9.5 nominal max mix, your 9.5 millimeter size, you have to have between 90 and 100% of that aggregate for it to be classified. It's got to go through all those points. Your angularity, that next chart down, basically there's a trend. As you increase the traffic level, you have to increase the angularity of the mix. Any ideas why?
Reduce rutting.
Reduce rutting, exactly. So they become more stringent as you go along. Flat and elongated particles, you know what that is. Just in age. Exactly. And then clay content, as you get more and more traffic, you want less and less clay fines in your material. And then down at the bottom, you got the mix design, which basically, again, you'll notice a trend that as you increase temperature, or as you increase as you increase traffic, or as you increase the design temperature, you're going to increase the number of design gyrations. I wouldn't really focus on the end initial and the end max, but the end design is the big one. Why would you increase your gyrations as you increase traffic or as you increase temperature? What?
Right.
compaction, yes. Think about it. So when you design an asphalt mix, you design to how many % air voids? 4. So basically the idea behind SuperPave is you pick all these things, your gradation, all this stuff, and you run in there to the end design gyrations, and you want to adjust the binder content so that you hit 4% air voids. And because at that point, all you're doing is either reducing, as you add more asphalt, you're reducing the air voids because you're just filling up airspace with binder, and vice versa. So as you compact more, that thing gets, especially when it gets smaller, the asphalt that you had in there now takes up more of the air space, correct? So your air voids, say you were at 5 and you increase the design gyrations, you may drop to 4.2 just by increasing the compaction. So we want to target 4. So basically what happens is, as you increase the design gyrations, to stay at 4% air voids, you've got to take some binder out because you're compacting it in more dense form. What would taking binder out help with? Rutting. So if you got high traffic and lots of loads and you have less binder, you're less likely to have rutting issues. So that's where that concept comes in. Same thing, as the temperature increases, you increase the number of design gyrations, which effectively means you end up taking more binder out later. And you have less issues with rutting, which would be good because you've got a higher design temperature. As far as everything else, there's not really much to say about that. So, does that recap that okay?
Yeah.
Alright. Let's see. I guess, nominal max aggregate size. Just because somebody taught me really hard on this in materials lab one day. Keep in mind that you would go to the first sieve size that retains 10% or more, and then you go up one, and that would be your nominal max. So if you had, you had 95% passing, 9.5 millimeter sieve, and then you go down to the number 4 sieve, and you had 89% passing, that means you had 11% retained on the number 4 or above. So you would take the number 4, you add 1 to it, you go back to the 9.5, that's your nominal max. Your max would be 1 more, 12.5. It is not, I don't remember what that person tried to tell me in the lab, but it's not that. One other thing to note about the PG grading system, just notice the criteria stays constant regardless of what temperature you're at. The temperature fluctuates, but the standard is the same. So that dynamic shear, 1 kPa minimum, it stays the same, and you just adjust the temperature that you graded at depending on whether or not it meets that criteria. And it's really the only place you can come in. Alright, so good. Any other questions?
Thanks.
Thank you.